Welcome to Colligative Properties Part 1. In this video, we are going to discuss first the definition of colligative properties, and then secondarily we're going to define the freezing point depression and work through a couple of sample problems. So first, our definition of a colligative property is simply a property of a solution that depends on the quantity of solute particles and not on their identity. So what that means is that we could add 50 grams of sodium iodide, 50 grams of lithium chloride, 50 grams of potassium bromide, or 50 grams of rubidium fluoride to a solution, and they would all have the same effect on their colligative properties. The two colligative properties that we're going to talk about in this class are first freezing point depression and second boiling point elevation. Both are very pertinent things that we like to use, particularly in the Midwest when it snows. So by adding particles to our water on the roads, we are able to hopefully reduce the freezing point of that water to a temperature that is below the current atmospheric temperature. So freezing point depression is defined as the difference in freezing point. And again, freezing point is defined as the point at which a liquid slows to a solid. So that is a temperature. So the freezing point of a solution relative to the freezing point of the pure solvent as a result of an increase in quantity of particles in the solution. And we're actually able to calculate what this change in freezing point is going to be by using the following equation, which is delta TF equals I times KF times little m. And of course, this is where in math class delta stands for change. So that means this is the change in freezing temperature. Change is delta. I is the number of ions in the solute. We'll come back to this one in just a second. And then KF, I am convinced that chemists, they're great with numbers but not so great with language, because it seems as though they think that the word constant is spelled with a K, because oftentimes constants are abbreviated with the letter K. So this constant is the molal freezing constant of the solvent. All right, now for our sample problem. First one is that antifreeze helps to prevent a car from freezing. That would be bad if a car froze. So we add antifreeze to the engine. What is the freezing point depression of a solution that contains exactly 100 grams of ethylene glycol in half a kilogram of water? Now, the chemical formula for ethylene glycol is C6H6O2, and the KF for water is 1.86 degrees Celsius per molal. Now, I said that we would come back to the letter I for ions. Now, ethylene glycol, C6H6O2. In order for it to be an ionic compound, we need to have a metal and a nonmetal, or a cation and an anion. We have neither. This is a covalent compound. So, for all covalent compounds, I is 1. So in this instance, I is going to be 1. Next, Kf, they gave us Kf as 1.86 degrees Celsius per molal. And then our molality, they did not give us. We have to calculate that. So again, molality is defined as moles of solute over kilograms of solvent. Since we do not have the moles of the solute, we are going to start with our 100 grams of ethylene glycol, which is C6H6O2. And then we need to calculate our molar mass of ethylene glycol. In order to do that, we know that carbon has a molar mass of 12.01 times 6 plus hydrogen has a molar mass of 1.01 times 6 plus we know that oxygen has a molar mass of 16 times 2. So that means that our molar mass of ethylene glycol is 110.12 grams of C6H6O2 per 1 mole of C6H6O2. 100 divided by second answer gives us 0.91 moles of C6H6O2. So that means that our moles of solute is 0.91 moles over our kilograms of solvent, which is 0.5 kilograms, gives us a molality of 0.91 divided by 0.5 gives us a molality of 1.82. That's moles per kilogram, or also known as 1.82 little m. Now, when we look at our equation again, delta TF equals I KF times m. That means that delta TF equals I, which is 1, times Kf, which is 1.86 degrees Celsius per molal, times 1.82 molal. That means that delta TF is 1.86 times 1.82 times 1, which gives us a freezing point depression of 3.4 degrees Celsius. Now, that's not our new freezing temperature, but instead, that is our change in freezing temperature. So if we were to calculate our freezing temperature now of the water, we know that the initial freezing temperature of water is 0 degrees Celsius. Our change is 3.4, and that's a negative change because it's a depression. When I think of depression, I think it's getting lesser. So 0 degrees Celsius minus 3.4 degrees Celsius gives us a new freezing temperature of 3.4 degrees Celsius. That's our new freezing temperature, is negative 3.4. All right. So that's the first sample problem. The second one, our I is not going to be 1. So in order to ensure that the roads that we drive on are safe and sound when there is water on them and the water is at risk of freezing, we tend to add water or add salt to that water with the hopes of reducing the temperature at which the water on the roads freezes to a temperature that is lower than that of the current atmospheric temperature, because it is far safer to drive on relatively benign water compared to very hazardous solid water or ice, because it's much more slick. So suppose that the salt trucks that drive around town are designed so that 0.25 kilograms of salt is dumped per 1 kilogram of water. How will this affect the freezing point of the water on the roads? Now, salt, suppose that the salt that they're using is NaCl. That means that we have Na plus and Cl minus. That means that we have 2 ions in that compound. So that means that I is going to be 2. Kf is the same, so it's going to be 1.86 degrees Celsius per molal. And then our molality, again, we have to calculate this. Now, they gave us 0.25 kilograms. we need to convert that to grams. So that is 250 grams of NaCl over 22.99 is the molar mass of sodium, 35.45 is the molar mass of chlorine. So that means that our molar mass is 58.44 grams of NaCl per 1 mole of NaCl. We plug those into our calculator, we get 4.3 moles NaCl. Since our equation is moles of solute per kilograms of solvent, and we have 1 kilogram, that means our molality is also equal to 4.3 moles per kilogram. So molality is 4.3. So in our equation, delta TF equals I KF times M. Delta TF equals 2 times 1.86 degrees Celsius per molal times 4.3 molal. So when we plug it into our calculator, we end up with 2 times 1.86 times 4.3 gives us a new freezing temperature of 16 degrees Celsius. And that's our change in temperature. So that means that our new freezing point is negative 16 degrees Celsius is our new freezing point. All right. Please stay tuned for volume 2, which will discuss boiling point elevation. Enjoy.